Now let's go and look and see what happens when we add an electric coil. So we go back up, we click on electric coil, we come over, and now we've got our electric coil input screen. We need to input our voltage and phase. We can click up here and we could select, for instance, a 277 volt single phase coil. You'll notice over here on the screen that the heating flow rate defaulted back to our 175 CFM minimum flow, and of course that's not going to be enough for doing electric heat. We know we want to have 50% of the maximum as a good starting point, so we'll go ahead and put in 350 CFM, and then we have our choice of whether we want to have a 1-stage, a 2-stage, or a 3-stage heater. Now for small heaters, you typically can get good control with only 1 stage. 3 stages are really not used very often these days. That was more popular when pneumatic controls were being used, when you had to break the heat capacity into more steps to get accurate temperature control. With digital controls or analog electronic controls, it's possible to get very accurate control with a fewer number of stages. These days it's pretty rare to see more than 2-stage heaters being used. Now if sometimes we're asked if we can build a 10-stage heater, and that's really totally impractical because that would require 10 separate elements and all the controls to operate each of those elements. When situations like that come up, that's when it's best to suggest an SCR controlled heater. An SCR heater is going to give us the same functionality that we would get from an infinite number of stages of heat. So that's going to give us the ultimate in control there. Now one thing I like to do, this is just has to do with our selection software, I like to take the coil minimum leaving air temperature, which defaults to 85 degrees, and drop it down to 55 degrees because I don't like it when it interferes with my selections. And let's say we put in a requirement for 3 kilowatts. We could either let it calculate the number of kilowatts we need, or we could just input the number of kilowatts. Then we say accept, we say calculate, we pull up our selection, it comes back to a size 8 unit. You'll notice our minimum pressure dropped from that, I believe it was 0.21 with the water coil, back down to 0.04. So it has a little more pressure drop than the bare basic unit, but an electric coil has not nearly the pressure drop of a water coil. You'll see our radiated sound level went back to 24 where we started. Our discharge sound stayed down at 21 because the casing that we use for the electric coil also acts as a sound attenuator. Now if we look at the heat results, you'll see here that we've got a leaving air temperature of 82. So when I guessed it at a design kilowatt of 3, I guess I was kind of low there. But this might be a good selection if we were supplying air to linear diffusers along an expanse of glass. So now that we've looked at a single duct selection, let's look at dual duct boxes. Where do you find dual duct boxes? They're usually found in university buildings, hospitals, and university hospitals. These units are supplied with hot and cold air and can be used in non-mixing or mixing applications. They can also provide variable volume or constant volume airflow to the spaces they serve. Dual duct boxes without mixing chambers should only be used in non-mixing applications. These units would provide cooling or heating, but not at the same time. A mixing chamber is absolutely necessary for blending hot and cold air streams together. The standard mixing ratio for dual duct boxes is a 1:10 ratio, meaning that for every 10 degrees of difference in the hot and cold supply temperatures, there will be no more than 1 degree of temperature variation at the discharge duct. High mixing boxes are also available, and they provide 1:20 mixing, so you could say they blend twice as well. With the high costs of operating dual duct systems, the market for dual duct boxes is somewhat limited. There is, however, renewed interest in dual duct boxes for mixing conditioned air with air from dedicated outdoor air systems. In an application like this, an optional water coil at the discharge of the unit could be used for heating without the need to actually reheat. There are many terminal unit lining options available from manufacturers. Traditional or standard lining materials usually involve fiberglass products. All manufacturers offer half-inch and 1-inch dual-density fiberglass. This material has an R value of 1.9 or 3.9 in the most common thicknesses. Fiberglass has good acoustical properties along with good insulating properties, but many system designers are trying to get away from exposed fiberglass. For critical environment applications such as hospital operating rooms or laboratories, fiberglass covered with foil or dual wall construction is needed to keep any stray fibers out of the airstream. Luckily for engineers who want to avoid using fiberglass in any form, there are new materials that have all the good properties of fiberglass without any of the potential problems. Engineered polymer foam is available in several thicknesses. It contains an antimicrobial agent to resist mold growth. It also absorbs no moisture and has a cleanable surface. There are also natural fiber linings available in multiple thicknesses with either cloth or foil facing. It's important to keep in mind that the lining material choice could have either a positive or negative impact on the acoustical performance of various types of terminal units. As a general rule, the harder the facing is on a liner, the less sound it will absorb. This can increase the transmission loss through the casing, resulting in lower radiated sound levels, but it can also result in higher discharge sound levels. Softer linings are not as effective for blocking noise, but can provide somewhat lower discharge sound levels. Terminal unit controls have come a long way since the 1980s when I first joined this industry. Back then all we had were pneumatic controls and everybody knew how to work with them. We probably provide more technical service now than we did back then because they are rarely used in new buildings. These days pneumatic controls are usually only supplied on boxes being used to remodel or finish out buildings with existing pneumatic systems. Analog electronic controls are often an excellent choice for small buildings or situations where there's no desire to network or communicate with the controls. Analog controls can provide excellent airflow and temperature control and can also be balanced using nothing more than a voltmeter and a screwdriver. Any new construction or large building is going to require digital electronic controls. In order to achieve lead points for building control and energy optimization, digital controls are almost always going to be needed. Digital controls use the latest PID control algorithms to provide excellent airflow and temperature control. They're usually networked and become part of the building management system. For many years, the industry has been moving towards interoperability between control devices. BACnet compliant systems are rapidly taking over the building controls industry.